When you walk into a dense forest, you are surrounded by towering pillars of wood and sprawling canopies of green. Whether you are looking at a monumental redwood in California, an ancient oak in Europe, or a slender palm on a tropical beach, your brain naturally groups them together. We call them all trees. Common sense dictates that because they look identical in structure, they must share a common, tree-like ancestor. But from an evolutionary perspective, that apparent unity is misleading. In the strict taxonomic classification of life on Earth, there is no such thing as a tree. The word tree does not describe a botanical family, a genus, or a single branch on the tree of life. If you trace their genetic lineages back through time, a towering pine and a broad-leafed maple belong to deeply separate branches of plant evolution. What you are actually looking at when you step into a forest is not a family of plants. You are looking at a survival strategy. You are witnessing one of the most striking and repeatedly observed patterns in biology: convergent evolution. The tree-like form did not emerge just once. It has appeared independently, over and over again, across distinct lineages of plant life. To understand why the tree shape keeps evolving, we must first understand how difficult it is to actually be a tree. For the first few billion years of life on Earth, the land was barren. When plants finally crawled out of the oceans around 470 million years ago, they were small, fragile things, creeping along the damp earth much like modern mosses. But life is driven by competition. In the struggle for sunlight, growing taller could offer a significant advantage. However, building upward against the constant pull of gravity introduces serious constraints. To become a tree, a creeping plant had to overcome two fundamental challenges. First, it had to develop a system capable of transporting water upward against gravity. It had to evolve complex vascular tissues, the xylem and phloem, to move water from the ground up to elevated leaves. Second, it needed structural integrity. A stem of moss or a blade of grass cannot support large amounts of weight. Plants evolved a key structural component: lignin. This complex polymer reinforces cell walls and allows tissues to become rigid, forming what we recognize as wood. Any plant lineage that acquired these traits gained access to a major ecological advantage: exposure to higher light levels above competing vegetation. And because the advantage was so significant, entirely different groups of plants began arriving at similar solutions. The first massive forests on Earth would look completely alien to us today. Around 350 million years ago, during the Carboniferous period, the world was dominated by towering giants that were not true trees as we understand them now. Instead, the sky was occupied by ancient lycophytes, relatives of modern, tiny quillworts. Plants like lepidodendron, the famous scale trees, grew up to 100 feet tall, but they didn't have solid wood like a modern oak. Instead, their trunks were supported by a massive thick outer layer called a cortex, which held them upright almost like a rigid pressurized tube. They didn't produce seeds, they reproduced using spores, much like the tiny ferns on today's forest floors. Another dominant group were the calamites, giant relatives of the modern horsetail weed. These ribbed, hollow stalks rose dozens of feet into the air, forming dense, swampy stands. These early arborescent giants were an early expression of tree-like growth. They dominated the planet for tens of millions of years, trapping large amounts of carbon that, after their remains accumulated in wetlands, would eventually form the coal deposits still used today. But eventually, the climate changed, the swamps dried up, and these lineages disappeared. Yet the general form did not disappear with them. As the earth dried out, a new lineage of plants took up the tree form. These were the gymnosperms, the group that includes modern conifers like pines, spruces, and the mighty sequoias. They evolved true secondary growth, the ability to add rings of thick wood year after year, and they developed seeds, allowing them to persist in drier environments. For the entire age of dinosaurs, gymnosperms were the dominant trees in many ecosystems. But this was not the end of the story. More than 100 million years later, a completely different, unrelated group of plants appeared. The angiosperms, or flowering plants. Starting as small, weed-like shrubs, they entered the same evolutionary landscape. Driven by similar environmental pressures to access sunlight, these flowering plants independently evolved their own versions of thick, woody trunks and spreading canopies. Through convergent evolution, angiosperms, which include oaks, maples, birch and cherry trees, expanded into large tree-like forms. They adopted a broadly similar architecture to conifers, despite following a different evolutionary history. The drive to become tree-like is so widespread that some plants have developed alternative structural strategies. Consider the palm tree. It belongs to the monocot group, making its evolutionary lineage much closer to grasses than to an oak or a pine. Palms lack the traditional ring-forming vascular cambium that produces true wood. Instead, they achieve their height through the growth and organization of dense, fibrous tissues. Even bamboo is not a tree at all. Taxonomically, it is a true grass, belonging to the same family as wheat and corn. Yet, under similar environmental pressures, it can grow to impressive heights, forming dense, forest-like stands without producing traditional wood. And in places like New Zealand, ancient lineages of ferns still grow tall, mimicking the overarching structure of the forest canopy, using entirely different structural solutions. In evolutionary biology, there is a term for animals repeatedly evolving into a crab-like shape, carcinization. The plant kingdom presents a broader parallel, the repeated emergence of tree-like forms. A tree is not a single lineage. It is a recurring growth strategy shaped by shared constraints. Whether in ancient swamp forests, Mesozoic woodlands, or modern ecosystems, different plant groups have, at different times, arrived at similar structural solutions. When faced with the challenge of accessing light in crowded environments, similar forms have emerged again and again, each one part of a much longer evolutionary history.